Okay, so let's think about what it's going to take to actually build a hardware emulator for the beta instruction set. Well, the key to figuring out what an instruction does is shown here. Here's the 32-bit instruction word that we'll be fetching from the memory, which will hold both instructions and data. And it's the high order 6 bits of the opcode that completely determine the format of the remaining fields of the instruction and then what operation is to be performed. So our hardware will certainly look at the high order 6 bits of each instruction to determine what the operation is that we need to do. We actually have 2 different formats of instructions, one of which involves 2 register operands. So remember, we have a 32 element register file. There's 32 registers, each of which holds 32 bits. So it's a little array of these 32-bit locations, and there's 32 elements in the array. And we can basically reference 2 elements of the array, the RA register and the RB register. And then we can choose to write our result back into a 3rd element. So that's one format of instruction. We have a second format of instruction which is very similar, except that the second operand, instead of coming from the RB register, will actually come from be a constant that will be built from part of the bits of the instruction itself. And I'll say more about that in a second. So with these operate class instructions, we can specify a large number of arithmetic and Boolean and comparison operations, plus some shifts. And they all basically take 2 32-bit operands and produce a 32-bit result, which gets written into the RC field. In addition to the operate class instructions, we have a bunch of sort of, I don't want to call them miscellaneous, because they don't involve a numeric operation. But they really round out the capabilities of our machine. They let us load information to and from main memory and the registers. So that's load and store. And then there's 3 instructions, jump, branch equal, and branch not equal, that let us change where the next instruction comes from in memory. Normally we're just fetching instructions sequentially from memory, but we can change that with the jump and branch instructions. And finally, there's sort of a weird instruction called LDR that you'll talk more about in a section. Our approach for building the machine is going to be very straightforward. We're simply going to take a napkin, in this case a PowerPoint slide, and start drawing a data path, a collection of registers and multiplexers and memories. And we'll just keep adding features to that data path until we've come up with enough hardware to execute all of our instructions. Okay, so we're going to sort of go through the instruction set sort of group by group and build our machine. Our bag of components, we're going to have these registers, all of which will be pretty much 32-bit registers. So they take a clock, and on the rising edge of the clock, they load a new value into the register. We'll use multiplexers, and again, mostly they'll be 32-bit multiplexers. In other words, the data coming into them will be 2 32-bit words, and we'll get out a 32-bit word. This is a 2-to-1 multiplexer on the slide here. You'll see that we actually have other multiplexers. We have a 4-to-1 multiplexer and an 8-to-1 multiplexer. So all of which really, the multiplexers are a way of steering data around the data path. And you'll see that they're very handy for doing that. We have the ALU that you designed as part of Lab 3, which does all the heavy lifting of actually doing the arithmetic and logic operations. That's what ALU stands for, right? Arithmetic and logic unit. Also some shifts and some compares. And then finally some memories, and I'll talk more about the memories as they come up.